Hello, this is Mr. Best. Welcome to section 2.7, Graphs of Rational Functions. We're going to identify and graph slant asymptotes, and we're going to identify points of discontinuity. The other day we did vertical and horizontal asymptotes, and we're also going to start graphing some of the rational functions. We will be using the graphing calculator today to help us graph, but all the stuff that we're going to be finding is going to be found algebraically. We're only going to use the graphing calculator to help us find those additional points to make it a little bit easier. Alright, first thing, how are we going to find the intercepts? Alright, if we're looking for the y-intercept, go back to Algebra 1 and think about, what is the y-intercept? The y-intercept is when the graph crosses the y-axis, so x will always be 0. Okay, so we can just plug 0 into the function and find the output. So f of 0 is equal to 2 over 0 minus 3. And so that would be negative 2/3. So the y-intercept is at 0, negative 2/3. How do you find the x-intercept? Well, the x-intercept, where the graph crosses the x-axis, is when y is equal to 0. So now you're going to plug 0 in for the function, the output. So 0 is equal to 2 times x minus 3. Or sorry, 2 divided by x minus 3. And so how's that going to work? Well, you could multiply by the denominator, x minus 3. That will cancel on this side, and then the other side will just stay 0. So 0 is equal to 2. Well, 0 is not equal to 2, so on this one it looks like we have no x-intercept, which means the graph does not cross the x-axis at all. And that's perfectly fine with rational functions. So go back to the other day, vertical asymptote. Vertical asymptote comes from your denominator. What are the restrictions of your denominator? So x minus 3 is equal to 0. So if you add 3 to both sides, you'll get x equals 3. So your vertical asymptote is at x equals 3. And your horizontal asymptote has to do with your degrees. So the degree on top of the function x equals 0, or x raised to the 0, so 0 over 1. So if the degree is smaller on top than it is on bottom, then that means you have a horizontal asymptote of y equals 0. So we've kind of gone through the different things that we can find about the graph for now. And let's go ahead and graph what we know. Well, the y-intercept is at 0, negative 2/3, so it might be a little difficult to plot, but we'll get that idea down there. Whoops. That's no good. Okay, sorry about that. And then on the x-intercept, it doesn't cross, so we can't plot that. We have the vertical asymptote, so let's get that. I'm going to get my line to be dotted because it's not part of the graph. So at x equals negative 3, we have a vertical asymptote, and then the horizontal is at y equals 0. So we don't have a lot going on that we can actually graph from. So we know one of the graphs is kind of on the bottom left corner, and the other one's probably on the top right. But at this point, we've done the algebra. The only thing left to do would be literally just plugging in values into the function. And this is where I'm going to let you guys use the graphing calculator to kind of find some additional points. So we're going to look on the calculator at our table and see if we can find some additional points here. So let's go to the calculator. Plug in your function y is equal to 2 divided by x minus 3. You can go ahead and graph it. And you can see on here, now on mine it actually, you can see a little bit that it draws in the vertical asymptote. Yours probably won't do that, or it'll try to connect the graphs, and that's not really correct either. So, but we know at x equals 3 we have a vertical asymptote. We want to get some couple extra points. So we knew the graph was going to kind of look like this. You can see here where that y-intercept is we thought it was somewhere around, or we knew it was around negative 2/3. You can see on the top left corner it says negative 0.6 repeating, which is negative 2/3. So let's go back to the table and identify some points maybe that we can plot. So here's one. Excuse me. Here's one at x 1, negative 1. That seems like a pretty easy one to plot. 2, negative 2. We have 4, 2, 5, 1. If we need it, we have negative 1, negative 0.5, and 7 and 0.5 as well. So those are all points that we can kind of plot. So let's go ahead and do some of those. And so I kind of need both screens pulled up, but let's see. We had at x is 2, we were at negative 2. At 3, we didn't have one because that's a vertical asymptote. At 4, we were at 2, and at 5, we were at 1. Excuse me. So at x equals 2, we were at negative 2. At 4, we were at 2, and at 5, we were at 1. Let me go back and see if I can find maybe another one at x equals 1. At x equals 1, we were at negative 1, so I'll graph that one also. So at 1, we were at negative 1. And so that gives us a general idea of what that graph is going to look like. And there you go. So we're going to help identify the graph by finding all the important parts of it, but only use the calculator to help us actually graph the additional points. Alright, so one of the things that is in our learning targets is a slant asymptote and this points of discontinuity. And we didn't have anything on here. This was kind of a review of stuff that we've done, but then we did the graph. So let's kind of move to another problem where we're going to get some new information. So example 2, we're going to graph the rational function. We're still going to identify all the things that we just talked about. So let's go ahead and do that. One of the things we talked about the other day is we can't find the vertical and horizontal asymptote until we simplify the function. So on this one we can see that it can be factored. So let's go ahead and factor it. Make sure it is simplified. Alright, so once it's factored, we realize that there's a factor of x minus 3 that can cancel. And so we're left with x plus 3 over x plus 1. And so when we find the intercepts, let's go ahead and find the intercepts as well using that new function, x plus 3 over x plus 1. And so for, once again, the y-intercept, you're going to plug 0 in for x. So plug 0 in for x and you get 0. Let me do g of 0. You're going to get 0 plus 3 and 0 plus 1. So that's 3 over 1, which is 3. So we'll go ahead and plot that. 0, 3. That's your y-intercept. Alright, x-intercept, you know y is 0, so we're going to say 0 is equivalent to x plus 3 over x plus 1. We'll multiply by the denominator, and that will leave us with 0 is equal to x plus 3. And then if we solve that, it looks like we will get x equals negative 3 on that one. So we have an x-intercept at negative 3 comma 0. So we can plot that. We know the vertical asymptote comes from the denominator. So what value of x makes the denominator equal to 0? So x plus 1 equals 0, so therefore the vertical asymptote would be at x equals negative 1. We'll go ahead and graph that. The horizontal has to do with the degrees. Both degrees are 1. Change colors real quick to show you this. So degree is 1 here, and then you take your leading coefficients on both of those, it's also 1. So Horizontal is at y equals 1. We will graph that as well. Okay, and so right now we have 2 points and a horizontal and vertical asymptote. And so when we start to do that those additional points, we go to our graphing calculator to kind of identify what those additional points are. So let's do that. So we're going to plug in our new function. Do we plug in the original or the simplified? Well, that's a good question. What is going to be the difference here? Let's go ahead and plug in the original, x squared minus 9, because it's the original that we really want to graph. Is there going to be a difference between the original and the simplified? Okay, so let's go ahead and graph this. And so we see the vertical asymptote at x equals -1. It doesn't show the horizontal, but it looks like it's approaching that value of 1. We can kind of see where the x-intercept is and the y-intercept as well. And so let's get some additional points here. Let's go back to the table. Okay, and my table's all the way at 30 something, so let's get back here. Try to find some additional points here. We got -5 at 0.5, -4 at 1/3, -3 at 0, which we already had, -2 at -1, -1, there's the vertical asymptote, 0 at 3, which we already had, 1, 2, and then at 3, something's going on at x equals 3. I'm going to go back to the graph. At x equals 3, it's about right there. Now what's going on at x equals 3? It says it doesn't exist. I keep zooming in. I don't see anything. So what's going on there? Let's go back to the table again. So I don't know how I keep getting to these large numbers on the table. So what's happening? Alright, well, let's plot these points that we know. So let's get back. Let's plot some of these values that we already know. I need to go back and check, but I think -5 was at 0.5. -2 was -1. 1 was at 2. And then 3 was undefined. So I'm going to check that -5. I couldn't remember. So at -5, we're at 0.5. Okay. So let's plot these. What we have: -5. -5 is at 1/2. -2 is at -1. So that's 3 points on that side. That's pretty good. 1 is at 2, and then at 3, it didn't look like anything on the calculator was going on, but it's undefined. You know, so what's happening there? Well, there is something going on, and we know there's something going on because it was part of our restriction in the domain. Domain could not equal x equals 3. So what happens is there is a break in the graph, but the break is called a point of discontinuity. So a point of discontinuity, or hole, in the graph appears when the numerator and the denominator have a common term, which is exactly what happened. That's why we canceled it out. So there's a hole in the graph. So it actually, x equals 3, we have a break in the graph, but there's a hole, okay, at that single point. Now physically you're not going to be able to see it. That's why you couldn't see it on the graphing calculator. But when you go to graph it on your paper, I want you to make a little circle saying that there's a break in the graph. So our graph will look like this, and then on the top right corner there's going to be a break. There's going to be another break in the graph, not a vertical asymptote, but a hole in the graph. So where is that hole located? Well, since we don't really know from there, how do we find out where it is? Well, usually when we want to find out when x is a number and what y is, we plug it in. But if we plug it in, it's going to be undefined. But what if we plug it into not the original, but the simplified. Because in the simplified version it's not undefined, and so now when we plug it in, we get 3 plus 3 over 3 plus 1, and that's 6/4 or 3/2. So the point of discontinuity is going to occur at 3, 3/2. And so for some reason I tried to graph mine too soon, so I'm going to erase this part. And the whole actually is at 3, 1, 2, 3, 3/2, so that's 1, which is about right there. So I'm going to fix that. And there we go. And so now we're going to have to identify any points of discontinuity that occur while we're graphing as well. Alright, so that's another piece that we learned. And once again, the point of discontinuity occurs when the factors cancel. And so here's some guidelines that you can use to sketch a rational function. They're on page 152 in your textbook. It's really just the process that we just went through. We want to make sure that the function is simplified if possible. That has to happen on step 1. Once you do that, you can find your intercepts. Then you can find your vertical and horizontal asymptote. You check for holes and slants. We haven't talked about slant asymptotes yet. And then we're going to plot a couple extra points. So on this third example here, we're going to graph the rational function. Once again, we're going to go through those things. And as you can see, we have a new thing that's going to occur. I'm going to move that out of the way for now until we get to it. But let's go ahead and graph this just like we had planned before. We're going to go ahead and factor if we can. And we can take out a GCF. Nothing cancels. So what that means is we have no hole or point of discontinuity in this problem because nothing canceled. So now we're going to go through, find the y-intercept. So plug in 0 for x. So 0 squared minus 0 over 0 plus 1 is going to be 0 over 1. So the y-intercept is going to be at 0, 0. And then the x-intercept, you're going to plug in 0 for y and see what happens. So we'll get 0 is equal to the function. And what happens if we've done this, is going to be the third time that we've done this, is that we multiply by the denominator, and every single time excuse me excuse me, the denominator cancels. So really, every time that we set this up, we're setting 0 to equal the numerator. And if you go back and look at your guidelines, if you recognize this, to find the x-intercept, we're always setting our numerator equal to 0 because the denominator always cancels out. So on this one, the numerator actually is a quadratic, so we get two values. X can equal 0 or x can equal 1. So there's two x-intercepts, one at 0, 0, which we already knew, and one at 1, 0. So 0, 0 we already had, and then we have one at 1, 0. Alright. Vertical asymptote is at x equals -1 because x plus 1 cannot equal 0. So at x equals -1, we have a vertical asymptote. And a horizontal asymptote has to do with the degrees. Excuse me. And the degree excuse me. And the degree on this one, on top is 2, on bottom is 1. So the degree is 1 larger, so therefore the horizontal asymptote is none. We don't have one. And so when does this, with right now what we have a vertical asymptote, no horizontal, and 2 points. What's going on with this graph? Well, what happens is, with a slant asymptote, the graph of the function has a slant asymptote when the degree of the numerator is exactly 1 more than the degree of the denominator, which is exactly what we have. The degree on top is 2, the degree on bottom is 1, so it's 1 more than the degree in the denominator. And if this happens, then we have a slant asymptote, and how do we find it? We divide to find the equation. So here's another example where we're going to have to use some division, either long division or synthetic division. It all depends on what the problem is. Because if we have a quadratic divided by a linear, we can actually use synthetic division in this case. But we could also use long division. Either way is fine. So we'll do synthetic because I know that's the one you like the most. So if the factor of the divisor is x plus 1, then the negative 1 is what we put on the side. And then we have the numbers 1, negative 1, and 0. And so we do synthetic division, carry down the 1. Negative 1 times 1 is negative 1. We add, get negative 2. And then the remainder actually doesn't even matter. We're really just looking at what the linear function is that we're going to get when we're done. And we're always going to get a linear function because if we always take a degree of a numerator that is exactly 1 more than the degree of the denominator, you're always going to have a linear function, because if it's x to the third over x to the second, you will get x to the first every time. So what is this linear function? Y is equal to, remember you started at x squared, so this would be x, so y would be equal to 1x minus 2. And so we need to graph that for our slant asymptote. So at negative 2 would be our y-intercept, and then the slope would be 1. So you'd have that as your slope. So we'll have this as our slant asymptote. So now we need to go to the graphing calculator to identify the additional points that we need at this point. So our additional points, here we need to write a slant asymptote, y equals x minus 2. And then the additional points for this function. And so I have some of these written down, so I'll just write them down. Negative 2, negative 6, negative 3, negative 6, and I got 2 and 2/3. So, negative 2, negative 6, 1, 2, 3, 4, 5, 6. We also have negative 3, negative 6, so it must go up and then come back down. And then I also did 2 and 2/3, which is somewhere there. So let's go ahead and plot that and graph that function. And there you go. So you can take a look at that on your calculator and see what that looks like. Maybe get another point somewhere to the left of negative 1 to get a little bit more accurate graph. But that's how you identify your slant asymptote. So we've kind of gone through and identified how to find slant asymptotes now, how to find points of discontinuity when they occur. And so now when you're given a problem, you need to make sure that you're going through and identifying y-intercept, x-intercept, vertical, horizontal, slant, points of discontinuity. You're looking for all those things, and then when you need the additional points, you can plug it into your calculator and get this. I'm going to create a second video on this example. So if you want to try this problem and then click back to the second video, you can do so. If you feel pretty good about where we're at, you can go ahead and start the homework. These are all odds on this homework set, so make sure you read the directions on 55 through 57. Thank you.